Hello, hi everyone. Let's start. Today we will study first order logic. This is also called predicate logic. So, this either you can call it predicate logic or you can call it first order logic. And the questions that we will see, not the complete first order logic we will see. I hope that you already know the basics, like what is the definition of predicate, quantifiers, like what is a for all quantifier, what is their exist quantifier. So these very basic concepts, okay, the knowledge of these very basic concepts is required. So what I will discuss the model based questions. You might have already seen these questions in the gate exam. Okay, in gate 2017 there is a question, and in gate 1991 there is a question. Okay, so in NET exam also there is a NTA NET exam. So in that exam also 2-3 times, more than I think 3 or 4 times, they have asked question from this topic. Model based questions have been asked. So let's see what is this. Actually, once we study this topic, once this topic is over, you will see one thing, that this is not a new topic, right? It's not a brand new topic, because you already know the basics. If you already know the basics in a very nice way, if you understand all your concepts, then this is very easy concept. Okay, you just need to know what is the definition of model, and as soon as you know the definition, then you can very easily solve all these questions. But your basics must be strong. You must understand all these concepts, in a nice way. So now let's start. So first we will see the model based questions in propositional logic. You already know that. Let me just give you quick review. So we study something called mathematical logic. In mathematical logic we have different type of logics. For example, we have something called propositional logic. Okay, this propositional logic is a you can say is a type of logic which is very simplified. Okay, so next you can say next form of logic, more powerful logic that we have, more powerful than this propositional logic, that is called first order logic. We also have more powerful form of logic than first order logic. For example, second order logic, third order logic, fourth order logic, and so on. So there are many different type of logics that we have, but in our GATE syllabus we only have these two, propositional logic and first order logic. These two topics we have in GATE syllabus. You already know. Now let me just keep my discussion to these topics that are in the GATE syllabus. So let's talk about propositional logic and first order logic. This propositional logic is a very simplified form of logic. In this propositional logic, basically what are the things that we have? If you see, then in propositional logic you have something called propositions. So these are the propositions. Okay, some you can say more propositions you can have, P, Q, R, S, T, and so on. These are propositions. And you have some binary operators, or you can say some connectives, some logical connectives. For example, negation, conjunction, disjunction, implication, by implication, XOR, NAND, NOR. So these logical connectives you have, and these are your propositions. This is your propositional logic, nothing else. Okay, all these things will basically make your propositional logic. So if I talk to you about what is the language of propositional logic, then basically any formula that you can construct from these things, that is basically a propositional logic formula. So you can see this is a very simplified form of logic. These few operators, and these are propositions. Also, one more thing, if you have a propositional variable, basically this P is a propositional variable, and the domain of this P is only two values, either true or false. You already know this. A proposition, the definition of proposition, if you know, proposition definition is basically that proposition is a English sentence. Basically propositional is a sentence. Okay, does not matter English or Chinese or whatever. Proposition is a sentence which is either true or false. Okay, so that's why you can see, if you have a propositional variable, then the domain, what is the meaning of domain? Domain means what are the values that this P can take. For example, this P, this propositional variable, can only take one of these two values. Either it can be true or it can be false. No other value can be taken by this propositional variable. Okay, so this is your propositional logic, very simplified form of logic. But in first order logic, what we have? this propositional logic is actually very weak form of logic. Many English statements, many theorems, many results, okay, we cannot write them in propositional logic format. So we need a more powerful form of logic, and that is our first order logic. This is also called predicate logic. So in first order logic, we have all the features of propositional logic. I can say that this propositional logic is already there. All these features like propositions, negation, conjunction, all these operators, everything is already there. But we have some additional features. For example, we have something called predicate. We have a feature of predicate. We have a feature of quantifiers. Okay, and we have feature of functions, relations, many things we have in first order logic. So this first order logic is more powerful than propositional logic, because already all the features of propositional logic are already present, and some additional features. The most important features of first order logic are these. These are the most important features. What is a predicate, what is a quantifier, and these three things are the most important features of first order logic. Let's see. What is a predicate? I think you already know. For example, predicate is basically, we have a sentence which has some variables. For example, if I write px, x is even. So this is a basically predicate. Here this x is a predicate variable, and this is the property of x. I can say that x is even. So this is the property of x. Now this x is a variable. So what are the values that this x can take? For example, you can see right now I am saying that x is even. So of course, if I talk about the values that this x can take, then it is very natural that you will say that maybe we are talking about integers or real numbers. Okay, of course, if you have another, let's assume you have another predicate qx, x is male. Now when you see this statement, at that point of time, if I ask you what are the values that this x can take, naturally it will come to your mind that this x can take basically the domain of x is set of all people. So you can see here the domain means set, what are the values, what are the possible values that this x can take. Okay, so set of all people is the domain of x if we have this statement. And if we have this statement px equal to, if we have this predicate px equal to x is even, then what are the values that this x can take? Some, I think, integers, set of integers or set of natural number, like that. So this domain must be given in the question. Okay, if this is not given, then we cannot assume the domain. Basically we will assume that in the domain we have everything. Okay, anyway, all these things we will see in today's lecture. All these confusions will be over. But this is a simple, very simple definition of predicate. Then we have two quantifiers. For all quantifier, there exists quantifier. For all quantifier basically says that if you have a variable x, and let's assume this is the domain of x, these are the values that this x can take. Now if I say that for all x this px must be true, if I say this, basically I am saying that for all x this px is some predicate, this px is some property of x. And now if I say that for all x px must be true, what it means? It means that for every value of x, this is the domain, remember, these are the values that this x can take. So for every value that x can take, this px must be true. This is the meaning of for all quantifier. This for all quantifier is talking about every possible value that this x can take. And this for all quantifier is saying that every possible value that this x can take, or you can say that every value from the domain of x, for every value this px must be true. Okay, for example, what is this there exists quantifier? This quantifier is saying that if I want to say that, let's assume I want to say that for at least one value, this is the domain, in this domain for at least one value this px must be true, then I will write like this: there exists x px. Here I am saying that for at least one value, for some value in this domain, this px must be true. So you already know all these things because of course you are in the final phase of GATE exam preparation. So this is a very natural thing that you already know these basics. So let's move on and let's go to the topic that we are going to study today, and that is our model based question. So first we will see what is the definition of model. What is this thing? What is this model thing? So when we talk about model, automatically few things come with it, and one is what is interpretation. So we need to see basically these two concepts. Once these two concepts we see, automatically all these questions you can very easily solve. So first we will see these concepts in propositional logic. Remember, in propositional logic we do not have quantifiers. In propositional logic we have some propositions and we have some logical connective, and every proposition has the domain. This is the domain of every proposition. This is the very simple domain. Okay, every proposition can either be true or it can be false. So this is the domain of every propositional variable. When I say this P is basically a propositional variable, but sometimes I will say that this P is proposition, because you know that this propositional variable, this is representing some proposition. You have a proposition, maybe this P is a proposition that this is the discrete mathematics live class. So you can see that this P is representing a proposition. So this P is called propositional variable and this is called proposition, but we will use them interchangeably. Okay, so when I say that this P is a propositional variable, or so when I say that this P is proposition, both are same thing. Okay, now let's see. So the definition of propositional logic, you already know all these things. Wait a second. Yes. So let's see the definition of model from the propositional logic point of view. If you have a propositional logic formula, let's assume that your formula is f is let's call it g. So your formula is basically, let's assume p or q. Okay, and this p comma q, these are your, you can say these are your propositional variables, and this is your disjunction. Now if you see this formula and you make the truth table, then very easily you can make this is the truth table of p or q, p disjunction q. So the truth table will be what? This will be the truth table 0 1 1 1. This is your truth table for p or q. Remember, when I am writing 0, basically 0 means false and 1 means true. So instead of true comma false, I am writing 0 comma 1 because it will save time. Okay, so anyway, now you can see when I'm here, p is false, q is false, then this p disjunction q, this also will become false. Now in this example, let's see what is the meaning of interpretation. The meaning of interpretation, the definition of interpretation is very simple. What are all the things that you require to say the truth value of g? So this is the definition. Basically, if I ask you, let's assume I give you this formula and I ask you what is the truth value, I directly ask you what is the truth value of this truth value. Then what you will say? You will say that I cannot tell you truth value because I don't know what is the truth value of p, what is the truth value of q. So you can see directly you cannot say what is the truth value of p and q. But if I give you this information, I am giving you some information that p is true, q is true. Now if I ask you what is the truth value of g, you can very easily ask, you can very easily answer. You will say that truth value of g is true. So you can see this is interpretation, you can say. So interpretation, very intuitive, very informal definition. If you see, then the definition is this. What is the information you need to find out the truth value of a formula? This is your formula and you want to find out the truth value. Then what is the information you need? Only this much information is needed. So this is the interpretation. For example, this is also another interpretation. If you have this interpretation, in this interpretation, the value of g will be false. You can have different interpretations. How many different interpretations you can have? So in propositional logic, very easily you can find out how many different interpretations you can have. For example, if you have a formula g, p and q, then tell me how many interpretations are possible. Only 4 interpretations are possible, and those 4 interpretations, like this is first interpretation that is possible, this is one possible interpretation, okay, this is another possible interpretation, okay, this is another possible interpretation, and this is another possible interpretation. Only these 4 interpretations are possible for this formula. So hence I can say for this formula g, there are total 4 interpretations. Okay, now so this is the definition of interpretation. Now let's see the definition of model. Okay, the definition of model is also very simple. Such an interpretation, okay, for which formula is true. That is called model. For example, in this formula, if you see, for this interpretation, let's call it I0 interpretation, and let's call it I1 interpretation, let's call it I2, and let's call it I3 interpretation. You can see that for these three interpretations, the formula is becoming true. Hence, we will say these three interpretations are model. So how many models we have for this formula? Total 3 models. For this formula, there are total 3 models and there are total 3 interpretations. So this is the very simple concept that we have in propositional logic. Remember, so far we are only talking about propositional logic, and this is all. So the definition of interpretation, if you want to write down, you can very easily, you can write down that if you have a propositional logic formula, let's assume G is a propositional logic formula, then what is the interpretation? Then the definition of interpretation is very simple. Interpretation means to every you can say this proposition that is involved, to every proposition you must give some truth value. Like if you want to give me interpretation for a formula, then what you need to do, for every proposition you need to give me what is the truth value of that proposition. For every proposition, truth value given. So this is the simple definition of interpretation. And what is the definition of model? Model is an interpretation for which formula is true. An interpretation, okay, an interpretation for which G is true. This is the simple definition of interpretation, and this is the definition of model. Now you can answer these questions. Let's see this question. This is a NET exam question, remember, this is a previous year NET exam question. Let's see, he is saying, consider a vocabulary where only 4 propositions are there. So basically these are the 4 propositions that we have, A, B, C, D. How many models are there for the following sentence? This is a NET exam question. So this is the formula that is given to you. So tell me, how many models are there for this formula? What will be the answer? Try this. Very easy. You already know the definition of interpretation and you also know the definition of model. Now, what will be the answer? So let's see. You can see, first of all, let me tell you, this is your 4 propositions you have, basically A, B, C, D, 4 propositions you have. Then how many rows you have in the truth table? Total 16 rows will be there in the truth table. Remember, when we talk about propositional logic, then every row is every row is an interpretation. For example, this is an interpretation. Every row is an interpretation. For example, this is an interpretation, because interpretation definition is simple. To every proposition, you must assign truth value. So you can see this is one possible interpretation. This is another possible interpretation. This is another possible interpretation, and so on. Total 16 rows we have in the truth table. Every row is an interpretation. So how many interpretations you have? Total 16 interpretations you have. Okay, when you have 4 variables, then these are the possible interpretations. Now, those interpretations for which this formula will become true, those interpretations will be called model for this formula. So model for this formula means those interpretations for which this formula will become true. Now let me see this formula. If you actually look this formula you can write like this also: A and B and C and D complement. This is how you can write it, because actually this is just De Morgan formula you are applying. If you apply the De Morgan formula, then both are same. Now you can see, I want to make it true. Let's call it G. I want to find for how many interpretations this G will become true. Okay, so this G will become true means this will become false. So I want to find for how many interpretations this will become false. You can very easily see that this will become false for 15 interpretations. This will become true only for one interpretation. This is true only when all are true. A is equal to B is equal to C is equal to D is equal to true. When all are true, then this will be true. For all other interpretations, for 15 interpretations, this formula A and B and C and D, this will become false. Because this will become false, so our main formula G will become true. So you can say for 15 interpretations, this G will become true. Hence, we have 15 models. Answer will be 15. So very easily, you can answer it. This is the question of previous year NET exam. This is a nice question actually. Now you will see more nice question, you can say. Now we have a, basically he's saying in the what is the definition he's saying in the question. Okay, let's solve this question. He's saying that, again, this is a NET exam question. So he's saying that you have 4 propositions A, B, C, D. Okay, in your system, basically in your system you have 4 propositions. Now he is asking how many models are there for the sentence B or C. Tell me what will be the answer. Yes, Naim, that is correct. If we have n propositional variable, then there will be total 2 power n interpretations will be there. Okay, and out of those interpretations for which our formula will become true, those will be called model. Now what will be the answer for this question? Anyone? Yes, so let's see. Okay, first of all, some of let me tell you, when some students see this formula B or C, what they think that how many models will be there, they directly say that B or C, so 3 models will be there, but there is no option here. You can see 3 is not the option. So somewhere you are incorrect, somewhere you are making mistake. And what is that mistake? Let me tell you what is that mistake. See, this is a simplified formula. Okay, you have total 4 variables, but your formula is B or C. This is your formula, but you have 4 variables. It's like this. In digital logic, many times you see this. Let's assume in digital logic we have a function, and this function is ABC. This is a function. Basically there are total 3 Boolean variables, and let's assume this function is like this. For every row, this function is basically you can say is like this. Let me write it. Okay, let me, for example, for these rows 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Let's assume this is your function. Function is basically 0 0 0 0 and then 1 1 1 1. Now if you look at this function, okay, then this function is basically just A. Remember, when you minimize this function f, then what you will get? You will get A. So remember, when I give you a formula, let's assume in digital logic, if I give you a function, if I give you a Boolean function like this, then it does not mean that we have only one variable. We have only one Boolean variable. This Boolean function is basically defined for 3 Boolean variables, but the output is always A. So it's like this. This function is like this. This function is taking 3 inputs, A, B, C, but the output is always determined by A. So the output is always A. This B and C, they are basically useless. You can say they are useless. So that is the point. So just because your formula is involving only one variable, that does not mean that your function is defined for only one variable. Your function can be defined for more than one variables. Okay, but this is a simplified form. So similarly here, you can see our system basically that has 4 propositions, but our formula, in our formula, you can say A, D, they are useless. But when you see how many propositions, when you have total 4 variables A, B, C, D, then how many interpretations will be there? Again, total 16 interpretations will be there. Okay, out of these 16 interpretations, for how many interpretations this formula B or C will become true? Let's find out. So you can see that this B or C, this will become true in three cases. This B comma C, when basically when either this B is true or this C is true or both are true. So in three cases this B or C will become true. And remember, A comma D, these are basically don't care, we don't care about their value. So we have two possible value here, two possible value here. So finally, how many? Total 12 interpretations, total 12 models will be there. This is how you can find. Is there a way without truth table? Yes, of course there is way. Like this is the way using combinatorics. I want to find for we have total 4 variables A, B, C, D, and I want to find how many interpretations this will become true. Very easily I can apply the combinatorics. I can apply, because what I can do, this B or C, they both can be assigned in 3 ways. You have 3 ways for them. Either both can be true, or B can be true, C can be false, or C can be true, B can be false. So 3 ways you have for B comma C, 2 ways you have for A, and 2 ways you have for D, because this E and D, they do not matter. So you can assign them any value, true, false, whatever value you want to assign, you can assign. So finally you can apply the product rule of you can say combinatorics. Then what will be the answer? For 12 interpretations, this formula will become true. Or you can solve it like this. Okay, there is another way to solve it. What you can find out, you want to find for how many interpretations this will be true. So just find the total and minus when it will be false, when this will be false. So total is 16 minus when it will become false. It will become false when this B comma C will become false. And remember, A comma D, they do not matter. So you have 2 ways for A, 2 ways for D. So in total 4 cases, this formula will become false. So answer will be 12. Very easily you can, very easily, like basically you can apply any method. For any question, you have many method. You can apply any of them. Okay. So answer will be 12. But the mistake, okay, you just don't make this mistake that let's assume this is a NAT type question. Let's assume this is options are not there, and this is a NAT type question. So you need to write down the value. Then do not write 3. Many students will write down 3. Do not write 3. Answer will be 12. Okay, because this is a simplified formula, and remember we have A comma D also. Okay, so that is the point. Okay, let's see the next question. So these questions also you can very easily solve. These are also NET exam question, all of these. So you can see in NET exam, this type of model based questions have been asked many times. Okay, and these are nice questions actually. GATE should also ask this type of questions, and GATE have asked 2 times. But of course they can ask, you can see this GATE exam also can ask these questions very easily. Like, so these questions you can solve very easily. You can take them as a homework. Okay, and we will now move on to our discussion. So like these formulas. Okay, so you have these formulas, and how many models will be there in this question? He is saying that you have total 4 propositions. How many models will be there? Okay, so very easily you can answer. Like for example, this for A, this answer is here actually. If you see, this is your formula, this A and B or C and D. For this, we want to find out how many models will be there. So if you want to solve using truth table, of course, you should not do it using truth table, because truth table is a very time taking thing. But just to show you the, you can say, just to teach you the concept, I have taken this truth table. In this truth table, you can see that this. For these interpretations, you can see this formula is true. Hence, what will be the answer? Number of models will be 7. There are 7 models for which this proposition will be true. But of course, you do not need to solve it using truth table. You can very easily solve it using just direct your combinatorics. Your combinatorics says that when it will be true when what you can do, you can just find out a total minus when it will be false. Total is 16 minus when it will be false. It will be false when this is false and this is false. So this should be false and this should be false. When is this false? This is false in 3 ways. and this is false in 3 ways. So total 3 into 3, 9. So total 9 ways are there to make it false. So answer will be basically 7. You can see. So you can apply combinatorics, simple combinatorics, nothing else. So this is how you can find out. So for this formula we have total 7 models. For this formula we have just find out answer will be 12. For this A or B we have already done. And for this you can take as a homework. You can try. Okay. Like that. Yes, inclusion exclusion principle. Basically the subject, if you see this combinatoric subject, this is a subject which is providing you tools. In this combinatoric subject you have many tools, and just using those tools you need to be able to find out which tool to apply. Most of the time you can apply product rule. So this product rule you can apply most of the time. Sometimes you can apply this pigeonhole principle and inclusion exclusion, but most of the time you can see, almost you can say 70% of the time, this product rule, summation rule, these basic rules, product, summation, division, these principles you can use. Okay, very rarely they will ask you pigeonhole principle question, but just by reading the question you can in the GATE exam, actually this pigeonhole principle is a very famous principle, and the questions can become very hard, but in GATE exam they will ask you easy questions. Just by looking at the question you can find out whether to apply this pigeonhole principle or not. Okay, similarly this inclusion exclusion, but basically this combinatorics is a set of tools. You must practice it so much that you become very, you can say, confident. Like just by reading the question you should be able to find out which method to apply. Okay, let's move on. So this was the now we will study first order logic. This concept that we have seen, this model and interpretation, these concepts, now we will study from first order logic point of view. So let's assume, okay, let's start. Let's assume I give you this formula. I give you a formula G for all x px, and I ask you what is the truth value of G. Tell me, what is the truth value? Can you tell me what is the truth value of G? Now when I ask you the truth value of G, you will immediately say that I cannot say, because to find out the truth value of G you need some additional information. So now I will ask you what is the additional information you need. Tell me. So then you will tell me that I need, what is this px? First of all, I need this. Basically, what is this px? Then if I give you px, let's assume I give you px, that px x is even. Let's assume I give you this. Now can you tell me what is the truth value of G? Now also you cannot tell me, because you need the domain of x. So these two things you need. First you need domain of x, also you need this predicate. So this information if I provide you, then you can answer. For example, if I say that domain, let's assume the domain is basically a set of even natural number. This is set of even natural number. This is set of even natural numbers. Now if I ask you what is the truth value of G, what will you say? So you have px, you have domain. Now if I ask you what is the truth value of G, you can very easily answer. The answer will be basically true. Now you can say this is true, because our domain, this x can take, what are the values this x can take? X can take any natural number, any even natural number. So for every value of x in the domain, this px is true. Px is saying x is even. Say yes, for every even number this px is true. So hence I can say that in this interpretation, remember this is the interpretation. If you remember the definition of interpretation, this is your interpretation. So in this interpretation, our formula G is true. So this is your interpretation, and hence I can say this interpretation is a model for G. Are you getting the point? Because in this interpretation, our formula G is becoming true. So I can say that this interpretation is the model for G. This is a simple, the same definition of model, the same definition of interpretation we have used here. Let's assume you have a G. This is a first order logic formula. If this G is a first order logic formula, then what are the information you need to say the truth value of G? So you already know that basically we need the domain of every variable. Domain of every variable we need. whatever are the variables that we have in this formula. In this formula we can have maybe this formula is like this, 4 all x 4 all y, like this. So what is the domain of every variable that we need? Also, every predicate that we are using, we need to know what is that predicate. Basically we want to know what is that predicate. Or you can say that if you have a model, let's assume I give you this formula. Let's assume basically this formula I give you 4 all x px. Then if I give you this model, let's this domain, this is the domain, this domain D is given to you. Then what additional thing I need to give you? Additional thing is basically what is the value of p for every element. Basically, for let's assume this is element A, then I need to give you what is the truth value of this PA. If this element you have, then I need to give you what is the truth value of this, and so on. So either I can give you this px directly, I can give you that px is x is even, either I can do like that, or I can give you truth value of p for every element. This is what you require. So you require domain of every variable, you require the interpretation of every predicate in this domain. In this domain, let's assume this is your domain. In this domain, what is the interpretation of p for every element? This is also what you need. These things if I give you, then automatically you can find out the truth value of G. So that is the point. All this information that you have, this information is, you can call it, this information is basically your environment. Or you can call it, this information is called world. In this world, sometimes we will say that in this world, what is the truth value of G? This is what we will say. Or now actually you might be wondering why I am not calling it interpretation. You might be wondering like that. So let me tell you why I am not calling it interpretation. So what are the things that we are using? So this is your formula. For this formula, first I will give you a world. Okay. What is world? World means basically domain. I will give you a domain of x. Okay, let's assume this is the domain of x. So this is the world. In this world, in this domain, I need to give you interpretation of p for every element. So here I need to give you interpretation. In this domain, once I give you this domain, once I give you this world, then for every element I need to give you interpretation of every predicate symbol that we are using. Okay, everything that we are using, I need to give you interpretation of every predicate and everything that we are using in this G. I need to give you that. Okay. Now this complete thing, domain plus interpretation, this domain plus interpretation. Okay, domain and plus the interpretation of predicate in this domain. This complete thing we will call environment. So basically I will say that in this environment, what is the truth value of G? Because if you have this much information, then you can very easily answer what is the truth value of G. So this we will call it environment. I will say that in this environment, what is the truth value of G? So this is the simple. Okay, you don't have to confuse between these terminology. The terminology is simple. We need a domain. We need interpretation of every predicate in this domain. Now, if we have these two things, we will call it environment. And then I will say, what is the value of G in this environment? It will be clear. With example, it will be clear. Okay, let's take example. Let's assume first formula that I will give you, very simple formula. There exists x px. Now, for this formula, I am giving you environment. Remember, I am giving you environment E1. Let me give you environment E1. And this is the environment that the domain of x is a, b, c. And the interpretation is basically for the value of PA is true, the value of PB is false, and the value of PC is true. Now tell me, in this environment, what is the value of G? So value of G in environment E1. Tell me, value of G in this environment E1. That will be, you can very easily answer that will be true. Because what is this G? G is basically there exists x px. And you know this is the domain. So for at least one value, this px must be true. Yes. For A, this is becoming true. So I can say that in this environment, I can say the value of G is true. Now I can give you another environment. Let me give you another environment, like the domain of X is A comma B, and let me give you that PA is false and PB is false. This is the environment I am giving you. This is the complete environment. Now what is the truth value of G in this environment? That will be false, because G is saying that for at least one value in the domain, Px must be true. But the domain is this, and for none of these values, okay, for none of the values in the domain, P is becoming true. So hence I can say that in this environment G is false. From this what you can say? You can say that for this G, this environment is model and this environment is basically co-model. So you will say that this environment is model for G, model of G, and this environment is co-model of G. What is the definition of co-model? Co-model means such an environment in which our formula becomes false. So this environment is co-model of G. Okay, this E1 is model of G and this E2 is co-model of G. But you can see that for this formula G, we have model. There exists a model. Because there exists a model, so I can say that this formula G is satisfiable. Satisfiable means we can satisfy it. We can make it true. In some model, there exists a model. If there exists a model, then we can say that G is satisfiable. And remember, there exists a co-model also. Because there exists a co-model, so I can say that G is not always true. G is sometimes true, sometimes false. So if you remember this, sometimes true, sometimes false, what do we call it? We call it basically G is satisfiable, but G is not valid. G is invalid. G is satisfiable, but not valid. Remember, satisfiable means, in propositional logic also we have this word satisfiable. In propositional logic we say that a formula is satisfiable if it is true for at least one row. If it is true for at least one interpretation. If we have some interpretation in which our formula become true, then that formula will be called satisfiable. Here also we have satisfiable. Satisfiable means G can be true. Basically, G can become true in some environment. G can become true in some environment. Okay. This G can become true in some environment. This I can also say that for G there exists a model. For G there exists a model. If there exists a model, then we can say that a formula is satisfiable. So that is the definition of satisfiable. Now what is the definition of valid? Valid means always true. Valid means always true. A formula is valid means basically that is always true in all the models. Okay, so you can say that a formula is valid means that is always true, means there does not exist a co-model. Remember, there does not exist a co-model. Okay, so this is the definition of validity. This is the definition of satisfiability. Okay, and invalid means there exists a co-model. Satisfiable means there exists a model. Satisfiable means we can satisfy it. Somehow we can satisfy in some environment. In at least one environment, we can make G true. Then that will be called satisfiable. So this is the definition. Now you can see, this was our formula G. This formula G is satisfiable because we have a model. And remember, this formula G is invalid because there exists a co-model. Then model and satisfiable is same. Yes, a formula is satisfiable when there exists a model. Okay. So also when there exists a model, then the formula is satisfiable. Yes. So basically both are, you can say, both are almost, you can say same. One-to-one correspondence is there. If there exists a model, then formula is satisfiable. If a formula is satisfiable, then there exists a model. Every valid is satisfiable. Yes, every valid is satisfiable. Okay. So these definitions are also in the propositional logic also. These definitions we have. No co-model, then valid. Yes, if there does not exist a co-model, then our formula is valid. So okay, don't confuse. Very simple. Satisfiable means somehow we can satisfy it. Somehow we can satisfy it. Okay, means somehow we can make it true. Means there exists some model. There exists at least one model. Also, valid means always true. Okay, always true means in every environment formula is true. Okay, so with examples it will be more clear, don't worry. Now let's take more examples. Let's see these. So you can see these are the definitions: satisfiability, validity. A formula is satisfiable if it is true in some structure. You can call it structure, you can call it environment, you can call it world, does not matter. This terminology, okay, this is, you can say, okay, like this terminology can be different, okay, that does not matter. But the point is that you have a formula. This formula is satisfiable if it is true, for some environment, or you can say for some structure. If there exists no model, only co-model, then contradiction. Yes, if there exists no model, then we can say that our yes, basically contradiction is a word which we use in propositional logic. This word that you have, contradiction, this word we do not use in first order logic. I have not seen it, but yes, your idea is correct. Like contradiction means always false. So you can say that if there is no model, then we can say that our formula is unsatisfiable. You can call it unsatisfiable because contradiction means unsatisfiable. Unsatisfiable. Sir, what does this symbol mean? What is the meaning of this symbol? Yes, this symbol is a standard symbol for inference. This is a symbol for inference. Inference means, if I say, let's assume if I say that if I say this, then it means that A implies B. Or you can say that whenever A is true, then B is true. A implies B. This is basically a symbol of inference. Or you can say this B can be inferred from A. Or you can say that this B is true when A is true. If A is true, then B is also true. So this is the symbol of inference. This is called inference symbol. This is a standard symbol that we have. In first order logic, we use this symbol mostly. Okay. For example, if I write, let's assume I give you environment, some environment I give you, and I write like this. In this environment G1. For example, if you remember our formula G, this was our formula for all x. This was our formula. There exists x px. This was our formula. And for this formula, I gave you two environment, E1, E2. I can say that E1 inferred G. Yes, this is correct because in this environment G is true. I can say that E2 does not infer G because in this environment G is not true. So this is the you can say symbol for inference. In this environment G is true. In this environment G is not true. Okay, yeah, or you can say that when this is true, when this is the environment, then G is true. So this is the implication type of symbol. Okay, now let's see. So this is the definition of satisfiable. We have a structure. Satisfiable definition says that for some structure, for some environment, our formula is true. For some environment, some structure. Valid means for every structure our formula is true. Okay, whatever structure, whatever environment you have, our formula must be true for every environment. Okay, next, falsifiable means basically somehow we can make it false. Falsifiable means somehow we can make it false. So basically we can say that there exists a co-model. There exists a co-model. If there exists a co-model, then we can somehow make our formula false. And this is the definition of falsifiable. And you know what is unsatisfiable. Unsatisfiable means there is no environment in which our formula is true. That is the definition of unsatisfiable. Okay. So this is the definition, satisfiability and validity. Now let's see all these questions. First, you can see there exists x px. We have already seen this is satisfiable because we have already seen one environment in which this is true. So we have this is satisfiable. Why? Because we have a model. For example, what is the model? You can consider this model. Set of integers is the domain and px is like this, x plus x equal to x. What he's saying? He's saying that you have this, there exists x px. This is your formula G, and for this G he is giving interpretation and the interpretation that he is giving, the environment, the structure that he is giving is this, that the domain of x is set of integers, and this px is given to you, x plus x equal to x. This is px. Now tell me what is the truth value of g in this environment, in this structure. Consider this environment S. Then tell me what is the truth value of g in this structure, in this environment. So answer will be very easily, you can answer x plus x equal to x, set of integers. So this will be true because 0 plus 0 equal to 0. So there exists a value for which you can see. So hence we can say this structure, this environment is model for G. Hence we can say G is satisfiable. So you can say G is satisfiable. Remember, G is not a valid. He is saying that. However, the sentence is not valid. We have already seen this. There exists x px. We have already seen this is not valid. Why? Because you can have counterexample. What is the counterexample? One very simple counterexample you can give is where px is interpreted. One very counterexample, very natural counterexample is this. Let's assume here I am changing the domain. Okay, the domain is basically, let's assume, set of positive integers. If you have set of positive integers as a domain, then you can see in this environment this G will become false. Now he is saying x plus x equal to x. So you cannot take 1 plus 1 equal to 2. He is saying x plus x equal to x. So you need to see this. Px. The point is that for this formula we have co-model. For this formula we have a model. So this formula is satisfiable. This formula is not valid. This formula is falsifiable because we can make it false. We can make it false. We can make it true. All these things. Okay. You are giving a co-model. Okay. Now let's see this formula. He is saying for all x px or negative px. He is saying for all x px or negation of px. This is our formula. Now tell me, is this formula satisfiable, valid, all these things? Tell me what are the properties of this formula. Satisfiable, valid, invalid, falsifiable. What are the properties of this formula? So let's see. This formula is actually valid. This is valid. Why this is valid? Because whatever environment you take, whatever structure you take, for example, let's assume you take a domain. Let's assume I am randomly taking a domain A, B, C. Whatever domain you take, does not matter. Whatever domain you take. Okay. In that domain, for every element, okay, this will definitely become true. Okay, because whatever environment you have, let's assume you have environment E1 like this, that this A comma B comma C is there, and you can see environment means for every element I need to give you the truth value of P. Let's assume for A, PA is equal to true. For B, PB is equal to false. For C, PC equal to false. You can see that whatever environment you give me, whatever domain you give me, and in that domain, whatever interpretation you give me does not matter. You can see this for every element, this will be always true. Either this will be true or this will be true. Hence, I can say that this formula G is valid. Okay. Also, let me tell you one more thing, that in propositional logic, in mathematical logic, in this field of mathematical logic, domain is always non-empty. By default, domain is always non-empty. So remember, don't take empty domain. By default, domain is always empty. If they do not mention anything, then domain is always non-empty. You cannot take empty domain. If they explicitly say that, okay, you can take an empty domain, if they in the question they explicitly mention empty domain, then you need to take an empty domain. else always domain is always non-empty. So whatever environment you take, that must be basically non-empty environment. Basically in this domain there must be at least one element. Now you can very easily see this G is always true, so hence I can say G is valid. Remember, there does not exist a co-model. You cannot make it false. Whatever you do, does not matter what you do, you cannot make it false. So hence I can say there does not exist a co-model. Every environment is a model for G. Every environment is a model. So this is a valid, G is a valid. Let's see the next point. The formula, let's see this formula. Tell me this sentence: for all x px or for all x negation px. This is our formula. Tell me what is this? Satisfiable, valid, what is this? Formula G. So this formula is actually, yes, so this formula is invalid, but this formula is satisfiable. So this, I can say that this formula is satisfiable. I can say that this formula is invalid. Remember one more thing. There is something called scope of a quantifier. For example, if I write this for all x px, okay, then basically let's assume this is the scope. So every quantifier has a scope. Okay, let's assume I write for all x, and let's assume this is the scope of this this quantifier. This is the scope of this quantified variable. Then remember, out of this scope, okay, after this scope, if we, for example, okay, let's take this example. Okay, in this example you can see this is one and this is another, because the priority, if you see, the priority of quantifier is greater than these operators. If you see the precedence list, the list of precedence, if you see, then the highest precedence is given to bracket. So if you have a bracket, then that is the highest precedence. After that, we give precedence to negation operator. Then we give precedence to there exist and for all. These are the quantifiers. Then we give precedence to conjunction, disjunction, implication, by implication, like this. This is the precedence order. So the highest precedence is given to bracket and all these things. So you can see this quantifiers, they are given more precedence than these operators. So you can see here, if you see here, when I write like this, for all x px or for all x negation px, when I write like this, then remember this disjunction has less precedence than this quantifier. So this quantifier has more precedence. So what we will do, we will first do this. Similarly, this quantifier has more precedence, so we will first do this. So like this is like this. Now after this, what you can see, after this you can see one more thing. For all x px or for all x negation px, because you know this is one thing, this is another thing. So remember, this is the scope of this for all x, or you can say this is the scope of x. Scope of x is only this. Similarly, scope of this x is this. Now remember, this x has nothing to do with this x. It's like this. You have this is Rajasthan, and let's assume this is Delhi. So this is Rajasthan and this is Delhi, and in Rajasthan also you have someone called Deepak, and in Delhi also you have someone called Deepak. Remember, this Deepak has nothing to do with this Deepak. It's like that. So this is the scope of this x, and this is the scope of this x. So that's why this x has nothing to do with this x. Hence, don't confuse. And if you are confused, if you ever get confused, then you can very simply change this name of the quantifier. Basically, for example, if I write like this, for all x px, remember this name does not matter. This is a quantified variable, and this is just a quantified variable. The name does not matter. You can write it for all y py. Both are same. So if you are confused, then you can just change the name. Okay. So what I can do like this: for all x px or for all y negation py. Like this also I can do. Remember this thing. Wait a second. So what I'm saying, yeah, so I am saying that this has nothing to do with this. Okay, so and this formula is exactly same as this formula, both are exactly same, no change. So whether you solve this or whether you solve this, both are same. Okay, now let's solve it. So our formula G is for all x px or for all x negation px. Now I can give you very easily, I can give you a model. Let me give you a model, and the model is like this. This is the domain is a comma b, and what I'm going to do, for a this I'm going to make true, and for b I am going to make it true. Now you can see this environment that I have given you, this is the environment that I have given to you. This is the domain a comma b, and pa is true, pb is true. In this environment definitely g is true, you can see, because for this environment this will become true, this will become false, this g will become true. Now I can give you co-model also. For example, consider the co-model like this. Let's assume a comma b such that pa is true and pb is false. Consider this environment. So now in this environment, if you see this environment, in this environment this is also false, this is also false, so g will become false. So this is very easy example. So you can see this formula G, we have, there exists a model, there exists a co-model, so we can say that this formula G is satisfiable also, the formula G is invalid also. So this is how you can see. So this sentence is not valid, okay, but this is satisfiable. Now similarly you can find this. This is the next example. Tell me about this. There exists x, px and negation px. Tell me about this. Is this satisfiable, valid, all these things? You can see this is actually not satisfiable. This is not satisfiable because whatever you do, you cannot make it true. This G you cannot make it true because let's assume you take a domain, and in the domain, of course, I told you always take non-empty domain, because by default domains are always non-empty. So if you take any non-empty domain, whatever domain you take, okay, in that domain, for every variable you whatever the interpretation of p you define, basically whatever px you take and whatever domain you take, you can see that for every element this will definitely be false. This will be definitely false for every element. So hence I can say that for this formula G there does not exist a model. Hence I can say this is not satisfiable. There does not exist a model. This is very simple thing that you can see. So you can see this sentence is not satisfiable. Now remaining things you can see. Now let's consider this scenario. Let's assume that I give you a formula. Okay, you don't know anything about this formula, but I am giving you this, that you have something for all x and there is something psi. Okay, so for all x psi, this is a formula G. Remember, I am not giving you any information of psi. This psi is something, some first order logic formula. This psi could be anything. This psi is a first order logic formula, but you have this information that this is your G for all x psi. Okay, and I am saying that let's assume there exists a model of size 1. Let me give you this, that there exists a model of universe size 1. Universe size 1. What I am saying, basically I am saying that for this formula G there exists a environment in which this formula is true, and remember, in that environment the domain is only of size 1, means a single element. This is the information that you have. Now if I ask you, can you guarantee that for this formula G there exists a model of size 2? Can you guarantee this? For G, can you guarantee? Remember this word I am saying, Can you guarantee? Of course, don't. I don't think this is whether okay. This is spelling of guarantee, whatever. Can you guarantee that there exists a model of size 2? Can you guarantee this for G? So did you get the question? Question is very easy. Formula is given, G is given to you. Okay, and for this he is saying that there exists a model, means there is a environment in which domain is of size 1, in which this formula is true. Now can you guarantee that there exists a model of size 2? So just think about it. I will give you answer right now. So actually the answer, let's see the answer. Let's see what I will try to do. I will try my best to not get a model of size 2. Are you getting my point? Because what I will do, it is already given that this for this formula G there is a size 1. Let's assume that is A. Okay, this is your universe, this is your domain of X, and let's assume that for this domain this G is true. Basically you have some in this domain you have some interpretation of psi such that this G is true. Now I will try my best. Can I create a situation in which there does not exist any model of size 2? So you can very easily see this. Let's assume I don't know what is this psi, but let's assume this psi is X is 0. Let's assume this is your psi, X is 0. I don't know what is psi, but this could be psi. Psi could be X is 0. Maybe psi is just a px and this is saying X is 0. Are you getting this point? Now you can see if this is psi, then definitely I have a model of size 1. What is that model? You can see if this is the domain, then definitely G is true. So the given condition is satisfied, means for this formula G, for this I have a domain of size 1. You can see this is the domain of size 1 in which it is true. So this is I have a model of size 1. Yes. Now you can see that for this formula G, now if you create a universe of size 2, then this formula will not become true. You can see, because you can see this is your px and this px is already given, X is 0. Now if you create a domain of size 2, whatever you create, if you create size 2, basically 2 elements, if you take one, you take 0, other element you need to take. Let's assume you create you put any other element 1. When you put any other element other than 0, as soon as you put any other element, automatically this formula will become false, because this 1 is not 0. So hence you can see that when this information is given to you, that this for this formula G there exists a model of size 1, from that information you cannot guarantee that there will exist a model of size 2. This is this example clear? Let me know. This example is clear or not? So you can see this is a very easy example actually. Now we are going to take complicated examples also we will take, but first you need to understand this. What I did in this example, basically, first I satisfied the condition. This was the given condition. First I satisfied it. Then he was telling me, can you guarantee? Then I can say, no, I cannot guarantee, because I have given you a situation in which this is true but this is false. We do not have any model of size 2 for this formula. You can see, okay, for this formula we do not have any model of size 2, even though there is a model of size 1, but we do not have any model of size 2. So this is just a simple example. Now let's take little complicated example. Let's assume that you have a formula G, there exists X, there exists Y, psi. I don't have any information of psi. This psi could be any first order logic formula. Okay. Now for this G, let's assume I am giving you that for G, there exists a model of size 2. This is given, model of size 2. This is given to you. Okay. Now, can you guarantee that there will be a model of size 1? Can you guarantee a model of size 1? Can you basically, okay, I'm not writing again and again. Basically, this is given to you, model of size 2, this is given to you. Now, can you guarantee that model of size 1 will be there? Tell me. This is your formula. There exists X, there exists Y, psi. Can you guarantee a model of size 1? Actually, the answer for this also is no. We cannot guarantee. Because let me give you a situation in which we have a model of size 2, but model of size 1 is not possible. Let me give you a situation. Let's assume that psi is this. Let's assume psi is this. Px comma y. X is not equal to y. Let's assume this is psi. Now you can see that for this G, I have a model of size 2, 0, 1. This is a very clear cut example. I have a model of size 2. But for this G, there exists X, there exists Y, Px, Y. For this G, I cannot have a model of size 1, because if you take a size 1 model, basically if you take a size 1 universe, let's assume you take this, then automatically this will become false, because this Pxy will definitely become false. If you take this, there exists X, there exists Y, Pxy. So this X is also pointing A, this Y is also pointing A. So P A comma A, this is false. So you can say that if we have a model of size 2, then for this formula G, if we have a model of size 2, this is given to you, but we cannot guarantee that there will be a model of size 1. This we cannot guarantee. Is this example clear? We are going step by step. I am taking easy, then I am taking little harder. But this is what you need to understand, that basically just because you have a size model of size 2, that does not guarantee that G will have a model of size 1. But this should be given in the question X not equal to Y. No, this is not. See, that is the basic point. He is asking you, can you guarantee? He is asking you, can you guarantee? This is what he is asking. Okay, he is asking, can you guarantee? Of course, we cannot guarantee. Now I will give you one example where you can guarantee. Let me give you example. Let's see. It will be more clear with this example. Let's take this. There exists X, there exists Y for all Z psi. Let's assume this is the scenario and this is your Z. There exists X, there exists Y for all Z. Let's assume for G, this is given that a model of size 3 is there. Let's assume model of size 3. This is given to you. He's saying that for this G, we have a model of size 3. We have some model. I don't know what is that model, but we have some model of size 3. Now, can you guarantee that model of size 2 will be there? Can you guarantee model of size 2? This is information given to you. For G, there exists a model of size 3. Now, can you guarantee that there will definitely exist a model of size 2? This is the question. Let's think about it. So let me answer it. Okay, let me answer it quickly. So the answer is yes, we can guarantee that there will be a model of size 2. This we can guarantee. How? See, let's see. First, he is saying that we have a model of size 3. So model of size 3, let's assume you have a comma b comma c. Let's assume this is these are the three elements. Now in this domain, this is a model. Basically model means this will be true. So in this domain means a comma b comma c, a comma b comma c, a comma b comma c, and this psi is true. This psi is true. There exists x. Okay, you can choose whatever you want to choose. So let's assume you choose this. There exists x for whom there exists a y. Let's assume you choose this. For all z means basically he's saying that from here a, from here, and for all these. So he is basically saying that this psi is true for a b a. This psi is true for a b b. This psi is true for a b c. This psi is true for all of them. Okay, this is given to you. Now can you guarantee that there will be a size of 2? Yes, we can guarantee. And let me tell you what that will be. That will be actually your a comma b. This will be that model, that this will be that universe for which this psi will be true. Because you can see, if you have this a comma b, let's assume this is your domain. Now you can very easily see that this psi will become true. Why? Because there exists x, again a, there exists y, b, for all. Yes, a b a. You can again see, yes, for a b a, for a b b, this psi is already true. It is given a b a, a b b. This psi is already true. So again you can see, for this domain, again this psi will this g will become true. In this environment, when we take this a comma b, then this g will become true. So we can guarantee that there will be a model of size 2. This is guaranteed. We can guarantee that there will be a model of size 2. Is this point clear? Like what I did, let me tell you. If you see this formula, there exists x, there exists y for all z. If you see this formula, then this formula, for this formula he is saying a model of size 3. So model of size 3 means there exists element here. Let's assume that is a. There exists element here. Remember, that can be a also. That can be a also be. Let's assume that is a. Let's assume, because previously we have taken the scenario where a comma b. Let's take a. Now he is saying here every element a b c. Let's assume. So a comma a, and here every element. So means a comma for this, for a comma b, for a comma c. For these psi is true. This is given. This is given. Now also in this situation also I can guarantee that there will be a model of size 2. And what is that? What I will do, I will take this a, and I will take, so I will take, okay, actually I don't need to take any other element. I can also, in this situation actually model of size 1 will also be there, but the point is I can take a comma b. Now you can see in this domain you can very easily see a comma b, a comma b, a comma b. Basically there exists x, there exists y for all z. Again you can see this a, this a. So I can guarantee that this psi will be true in this domain. Is this point clear? Like, are you getting this point, what I'm saying? Let me know, is this point clear? That basically when you have for this formula g, this is the formula that I have taken for this formula g. If you have, it is given, if it is given that there exists a model of size 3, then definitely there exists a model of size 2 also. This model of size 2 I can guarantee. Remember, model of size 1 I cannot guarantee, but model of size 2 I can guarantee. Here also, remember, model of size 1 I cannot guarantee. For example, this formula, there exists x, there exists y for all z psi. If it is given that model of size 3 is there, model of size 3 is there. Now if he asks me, can you guarantee model of size 1? Remember that I cannot guarantee, because consider this situation that this psi is, this is like this. Let's assume ABC, ABC and ABC. And consider this situation that here A and here B, there exists A, there exists X, there exists Y, such that for everyone. Means basically, let's assume that for this ABA, for this ABB, and for this ABC. For these things psi is true. Now you can see that, so this was the given thing. Now can you guarantee that a model of size 1 will be there? No, we cannot guarantee, because if you take a single element, let's assume you take A, then you can clearly see that for this domain of size 1, this there exists x, there exists y for all z psi. This actually will not become true. Why? Because you have A here, A here, A here. Let's see whether we can. So there exists x, there exists y for all y. So for this A, A, for this psi is true or not? This psi is not guaranteed to be true, because you can see this psi can be false also. For this A. For this psi can be false also. So you can see that is the reason we cannot guarantee a model of size 1. This is the reason we cannot guarantee a model of size 1. Okay, if you want to understand it more clearly, let me give you one example. You can think about, you can think like this actually. There exists x, there exists y for all z psi. Just think like this. The way I am giving you, you can think like this. For every question you can think like this actually. Okay, what you need to think, let's assume this is a family. When he gives you, he is giving you that there exists a model of size 3. Model of size 3. He is giving you, let's assume in the question he is giving that there exists a model of size 3. When he is saying that there exists a model of size 3, you think about a family. In this family, let's assume there are 3 people, A, B, C. Now these 3 people are like this. There exists someone in this family. Who, basically there exists someone in this family. There exists someone else in the family. Basically these 2 people, they can take care of everyone. Are you getting this point? Basically there exists someone in the family for whom there exists someone in the family, such that together they can take care of everyone. It's like this. Maybe this is the father for whom there is mother, and now this father and mother, they can together, they can take care of everyone. So it's like this. Okay, remember, when they are taking care of everyone, then in this everyone, this father is also there, mother is also there, children is also there. In this everyone, basically this father mother pair, they can take care of children, they can take care of themselves, they can take care of everyone. That is the point. Okay, so you can think like this. Now he is asking that can we guarantee that there exists a model of size 2? Yes, we can guarantee. Just take this father and mother, because you can see this father and mother, they can take care of everyone. So you can say this father and mother, they can take care of everyone. Already they were taking care of everyone. Now when in the family, when there are only 2, let's assume unfortunately their children has expired, or maybe he has left them and he has gone to America, and this is some movie scenario. Okay, maybe some movie. Okay, he's not with them now. Okay, now you can see here also they were taking care of everyone. They were taking care of themselves also. Now here also they can take care of themselves. So okay, this is just an analogy, but actually let me tell you, this type of analogy helps me in solving all these type of questions. Whatever question you will give me, first I will think like this, then I very easily, in just within 1 minute actually I can solve the question using this type of analogy. So this will come by practice. Of course you can do this type of analogy and you can very easily see. So if you got this analogy, then the point is that if there exists a model of size 3, then definitely there exists a model of size 2 also. Okay, so that is the point. Okay, maybe I don't know whether you got it or not. So we will continue this tomorrow and I will take more examples. If you want to try, then let me give you some examples and you can take them as homework, and I will discuss them tomorrow. So the first homework is, let's assume I am giving you formula. Let's assume this is the formula for all x, for all y, there exists z psi, and for this the given model is of size 3. So it is given that model of size 3 is given. Now can you guarantee model of size 2? Can you guarantee model of size 4? So this is the question. If there exists model of size n, then n minus 1 is guaranteed. No, that depends on the formula. We have already seen in today's lecture, we have already seen two formula for which the model of size 3 was given, but the model of size 2 was given, but model of size 1 did not exist. So it depends on the formula. So let's take these homeworks. First homework is G is this: for all x, for all y, there exists z psi. Model of size 3 is given. Let's assume given. Now I am asking, can you guarantee model of size 2? Also, can you guarantee model of size 4? Also, can you guarantee model of size 1? So just check all these. Can you guarantee model of size 2, 4, 1? Which you can guarantee, which you cannot guarantee. So this is the first question. Second question, let me give you G. That is, there exists x, there exists y for all z, for all p psi. Let's assume that for this formula a model of size 3 is given. Now can you guarantee model of size 4, model of size 2, model of size 1? Can you guarantee these? Let's see the third question. For there exist for all. Yes. For that, yes. Shashank, for this formula, if you see for this particular, this type of formula, when you have this type of formula, there exists x, there exists y, there exists z, okay, there exists p, for all m, for all t. When you have this type of scenario where you have basically there exists, then you have some for all. When you have this type of scenario like this, and let's assume that you are given, they give you that there exists, if they give you that there exists a model of size greater than or equal to 4, if they give you, okay, if they give you that there is a model of size greater than or equal to 4, maybe 4, 5, 6, 7, does not matter. If they give you that there exists a model of size 4, then you can guarantee for this. If it is given, then you can guarantee that there will be a model of size 4. It is guaranteed that there will exist a model of size 4. For example, if it is given that model of size 5 is there, then model of size 4 will be definitely there. If there exists a model of size 10, then also you can guarantee that model of size 4 will be there. So why it is coming, actually, you can notice it. This is coming because of this. There exists x, there exists y, there exists z, there exists p. Because of this, I can guarantee that if it is given, then I can guarantee that model of size 4 also will be there. I can guarantee this. This type of example we have done actually, and this was your GATE question. GATE 2017 question was actually this. They have given this type of formula, and for that formula they are saying that there exists a model of size 7. Then they are asking, can you guarantee that there exists a model of size 3? Yes. So like that, you can solve the GATE 2017 question very easily. You can solve it. But I am saying that you don't restrict yourself to the GATE question. You should see the bigger picture. Because once they have asked a question in GATE exam, they are not going to ask the same question. They will change it. So you should understand the concept. Concept is more important. So that is why I am giving you these homeworks, and I will solve all of them tomorrow. Tomorrow I will solve all of them, okay? But you can try them. If you have any doubt, let's assume you have any doubt, then just re-watch this video, okay? Wherever you have doubt, I have already taken 3 or 4 examples. Just watch them and then try to solve them. But don't worry, tomorrow I will take all these examples and it will be clear. Everything will be clear. This is a very interesting topic actually. Okay, let's take more example. For example, for all x, for all y, there exists z, there exists p psi. Let's assume that they give you a model of size 2. Then can you guarantee a model of size 3? Can you guarantee a model of size 1? So these questions you can take. Any resources for this? Resources, actually exact resources I do not have, but I will share these slides. You can see in these slides many things are there. So I will share these slides, exact resources for these things. Like you will have to study from many different resources. You will have to study. I have studied more than 50 or 70, you can, sorry, 50, 60, I don't even remember. Many resources I have studied, many books. And finally, this complete all the things that I am telling you. This is basically the, you can say, compilation of all the articles, all the books that I have studied. Okay, so I would suggest that this video lecture, this is enough. Today we have seen many things. Tomorrow also I will discuss the remaining questions. Okay, the GATE question, GATE 2017 question, and that GATE 1991 question. Those also I will discuss, and these homeworks that I have given to you, these also I will discuss. Okay, so if there is something that you did not get in today's class, automatically you will get it next class. Okay, so don't worry. I guarantee, I promise you that you will get everything in the next class. Okay, but just work it out. Okay, just try it. Okay, whatever, if you get it wrong, if you get it right, does not matter. Just work it out. Okay, and tomorrow you can rectify your mistakes. If you are making some mistake, then tomorrow you will get to know where you are making that mistake, so that you will not make it again. That is the complete process of learning. So also please share this and graph theory slides. Okay, so in the Telegram group, I will share the all the slides will be shared there. Tonight you will get all these slides. Okay, so see you tomorrow. You can try these homework questions, and if there is any doubt, just rewatch the video. Just rewatch the video. Okay, tomorrow I will discuss all these things. Okay, thank you everyone. See you tomorrow.